morning, guys. Today we're going to really start focusing on probability. As you know and you've worked with before, there's two types of probabilities: theoretical probability and experimental probability. This is what you're most familiar with. This will we'll focus on a lot more as we get into our statistics and our probability distributions section. But theoretical probability, again, is what you're most familiar with. Probability of an outcome is the number of possible successful outcomes divided by the number of possible outcomes. So number of successes over total number possible. So for instance, a bag contains 3 blue marbles and 7 red marbles. What's the probability of drawing 1 blue marble? So again, probability, and I like to be very specific about what I'm looking for the probability of. The probability of 1 blue is equal to number of successful outcomes. So any of the 3 blues would be a success divided by the number of possible outcomes. Well, there are 10 total possible marbles. So 3 blues divided by 10 possible, and then you just go through and reduce. And again, I don't care what factor or what form you leave these in. If you want to leave it as a reduced fraction, that's fine. If you want to turn it into a decimal to a couple decimal places, that's fine. If you want to write it as a percentage, there's a 30% chance of drawing a blue marble. That's fine with me too. As long as you have some way of showing it's between 0 and 1 or between 0% and 100%, I'm not going to be picky on those things. So again, this is what you've worked with time and time again. Number of successful outcomes divided by number of possible outcomes. Experimental probability works kind of differently. We don't really care how many there are. What we care about is how many times we've executed this type of thing. We call those trials. So the probability of an outcome in experimental probability is the number of times this event has occurred, and then dividing that by the number of trials. So what percentage of the time did we get the outcome that we're looking for? So let's look at this one. Number 2 says a bag contains marbles. We don't know how many total, how many of each kind. We just know that there's marbles inside. You draw 1 marble, record its color, and then put the marble back. You repeat this 20 times, and of the 20 draws, 15 were blue. What's the probability of drawing a blue marble? Well, if we drew a blue marble 15 out of 20 times, we would say the probability of getting 1 blue marble is equal to 15 occurrences of a blue divided by 20 trials, 20 times we've drawn. So again, we can make that a reduced fraction. Let's make it 3/4. We can do it as a decimal between 0 and 1, or we can do it as a percentage. Any of those would be acceptable answers. So that's really, that's probability in a nutshell. Now, obviously, we have to make it a lot more complicated. Otherwise, we wouldn't be wasting our time doing this again. I don't know why I didn't write that up there. Oh well. So what happens when this thing gets more complicated is we start throwing in more things. What if we wanted the probability of drawing 2 blue marbles? Or the probability of drawing a red marble, then a blue marble? Or, a lot of different things we can throw into that. Or drawing 10 marbles and only exactly 4 of them are blue, and things of that nature. So those are where it gets a lot more involved, and that's where we're going to focus most of our time on. But if you will just keep in mind this general idea of number of possible successes over number of possibilities total, or number of successful occurrences divided by number of trials, then you should have a real good idea of what probability is, and we can put all these little tweaks on it that we're going to cover. So give me a second and we'll start talking about independent and dependent events. Okay, here we have independent and dependent events, which is going to be different from what we're talking about in a few minutes, called mutually exclusive and non-mutually exclusive. These either can affect or can't affect each other depending on certain conditions that we lay down. Independent events, obviously, are independent of each other. The occurrence of one event does not affect the probability of the other event. For example, drawing with replacement. So if I have a bag of marbles, take one out, calculate the probability, put that back, and then draw again. The first draw has 0 impact on the second draw because it didn't affect how many we get to choose from. Which is different from dependent events, where the occurrence of one event does affect the probability of the other event. So in that example would be drawing without replacement. So I draw a marble and then don't put it back and then go draw a second marble, obviously the first draw has affected the second draw because we have fewer marbles to choose from. So they're affecting each other. Now the idea is still the same as far as operation-wise. If I want the probability that this and that are happening, I'm going to multiply those two probabilities together. Now if it's independent, it's just probability of the first event times the second event. So for example, roll a red and blue number cubes, probability to get a blue 6 and a red even. Well, what happens on the 6 does not impact what happens on, or what happens on the blue does not impact what happens on the red. So we can just calculate them separately. So probability of a blue 6, well, there's 1 out of 6 of those. 1 6 out of 6 possible. And times probability of a red even. So a red one, again, the red doesn't have anything to do it, but the even, there's 2, 4, or 6, so there are 3 of those out of 6. So 3 out of 36, which is 1/12. So independent events, we just calculate them independently and multiply those two probabilities together. Now probability for dependent events says probability of A, then B. And the way we're going to, still going to be multiplying probability of A times this conditional probability. The way we read this is the probability of B given A. So we're going to figure out the probability of B, just like we did here, but we've got to put the conditions on there of what already happened to A. Let me kind of talk through what that means. In example 2 here, 12 marbles are in a bag, 7 are red and 5 are blue. What's the probability of drawing a red marble and then a blue marble if I don't put any together, or put that first one back? So the probability of a red times the probability of a blue given that the first one was red. Pretty simple. Okay, so probability of a red, there's 7 out of 12. It's a little ugly right there. So 7 out of the 12 were red times the probability of a blue. Well, how many blue ones are there? 5. Okay, drawing the red didn't change the fact that we have 5 blues, but it changes we don't have 12 to draw from, now we only have 11. So that's the conditional part. We've changed the total number we have to work with. So we go through, do the math, you get 35 out of, what's that, 132? And that's your answer. So it's the same idea, first event times the second event, but that second event's got a little stipulation on it, so we've got to make minor adjustments to see how that first event did affect the second event. Okay, so that's independent and dependent events, which can, may or may not affect each other depending on whether we've got some small tweaks, such as things that obviously can't have anything in common, or things that drawing with or without replacement. Now, number cubes can affect each other. For example, if I said, what's the probability of getting a 5 on the first, or 5 on one, and getting a sum of 3 on the other one? Well, or sorry, a sum of 8 on the other one, something like that. Well, we're going to assume our 5 is true so for the first one, so we know that the other one would have to be 5 plus 3. That would only occur one way if the first one is a 5. And we'll look at some more of those a little bit later on, a lot of them in class. But just because it says number of cubes does not automatically mean it's independent. Do a little analysis and say, does this first event affect the second event? If it does, it's dependent, and so we've got to make adjustments to our second probability. If it doesn't, then it's independent, and we just do the product of the two individual probabilities. Next, we will talk about exclusive and non-mutually exclusive events. That's things that can occur in the same sample space, but give me a second, I'll get that information up for you. So here we have it, mutually exclusive events and non-mutually exclusive events. These are events that we're not occurring one right after the other. It's kind of happening simultaneously, and they can either happen at the same time, have something in common, or they can't happen at the same time. I usually like to use deck of cards for these type of examples a lot of the time. But we'll look at a lot of different examples. Now, mutually exclusive events obviously are exclusive events that cannot occur at the same time. For example, this one right here, in a standard deck of 52 cards, that means ace through 10, and then jack, king, queen. So we have 13 cards of 4 different suits: spades, clubs, diamonds, and hearts. We'll use those a lot, so make sure you're familiar with a deck of playing cards. Now, if I was looking at a spade or a diamond, can a card be both a spade and a diamond at the same time? No, so that means that they are mutually exclusive events. So the way we would get that is probability of A or B is probability of A plus probability of B. So probability that I get one spade plus the probability that I get one diamond. Well, how many spades are there? We just talked about it. Ace through 10 is 10 cards. Jack, King, Queen is 3 more. So 13 spades out of the 52. So 13 out of the 52 cards are spades, and 13 out of the 52 are diamonds. So that's 26 out of the 52, which is 1/2, which should be intuitive. If I said, what's the probability that I get this suit or that suit? Well, that's half of the deck, so it should be a half. So that idea of or, okay, or is going to be an addition problem, okay, which is different from and. We looked at with the independent and dependent events. If I see an and, I'm thinking multiply those two things together. But if I see an or, it's an addition problem. I can have this happen or this happen, so we can have either one, so we get to add all of that stuff happen. Now this symbol right here should look familiar to us since we've been using it so much with our interval notations throughout the year. And that's that U, that's that union symbol. So we can look at it as A or B, or we can say A union B. A union B, which is the same idea, right? Think of when two people join in union, they add all their stuff together, right? So when you get married, there's a union of the two households and everything gets added together. Well, that's what union is. Okay, so union is an or. Those are interchangeable, so be familiar with both of them. And they just mean add up the two values. Now, if we had non-mutually exclusive, such as we have right here, where two events can occur at the same time, if I want the probability of one heart or one face card, well, I can have some hearts that are face cards. So since both of those can occur at the same time, we're still doing a union. It's an A or B, so it's still A union B, but because they're non-mutually exclusive, some places call it, some text you may see it say inclusive. Seen that a time or two. So since they're inclusive or non-mutually exclusive events, we've got to do a little adjusting to our formula, just like we did with the dependent events from the independent events. So it's still A plus B, but what we've got to do is we've got to subtract that overlap. And think about what's going on here. If I want the probability of getting one heart, well, there are 13 out of 52 of those. Let's make that look like a 3 or a B. Plus probability of getting a face card. Let's see, there's Jack, Queen, King. So 3 face cards, and there's 4 different suits, so 12 face cards. Well, the problem is, this is Ace through 10 plus Jack, King, Queen of hearts. This is Jack, King, Queen of clubs, Jack, King, Queen of spades, Jack, King, Queen of diamonds, and Jack, Queen, King of hearts. So the Jack, King, Queen of hearts got counted in both groups. So that's what this little tweak is. This little adjustment is minus probability of A and B. That's the intersection. That's the overlap between the two. Okay, so when we have non-mutually exclusive events, events that can both occur at the same time, we do the first event plus the second event minus the overlap. What did they have in common? Well, they had these 3 heart face cards that got counted in both groups, so let's subtract out one of those extra countings. So that's how we do it. And you go through, do the arithmetic. 13 minus 3 is 10, plus 12 is 22, over 52, which is 11 over 52. So there's your formula for non-mutually exclusive events. Probability of A or B, or we can say probability of A union B, is equal to probability of A plus probability of B minus the probability of both. Probability of both A and B occurring. And if you want, you can, it's an and, so we could technically take that and multiply it by that, and it should produce this overlap value. If you're having trouble actually reasoning through what the intersection is, what the in common portion is, you can just calculate it by multiplying the two probabilities together. So that's probability of A intersect B. This is a new symbol for us. We haven't used that yet this year. That U is the union symbol. Add the two together. This upside down U, that's our intersect symbol, and that means look at what's in common. And that intersect just comes from your Venn diagrams that you've worked with before. If I put all of my hearts in here, all of my hearts in here, and all of my face cards in here, there would be some overlap. So what we do is we just subtract out that intersection point. Okay, so this is the intersection. So add them up, subtract out the intersection. Where in a union, there's nothing in common, so we just add the two areas together. So you get the idea. Add those two areas together. So that was all our spades, that was all our diamonds. We add them all up and get our probability. So that's mutually exclusive, non-mutual. That should be 11 out of 26. I know some of y'all are yelling at your screen right now, so I'll fix that for you. Okay, 11 out of 26. Non-mutually exclusive, mutually exclusive. Give me a second, I'll get complements up here. So the last thing I want to talk about today is complement of an event. Now that's not complimenting an event, telling the event it looks nice, or you like the way its hair looks, or that it answered questions correctly. No, it's complement as in the rest of the stuff. What completes this? Think of complementary angles as being the angles that add up to give you 90 degrees. So if I know 30 degrees is one angle, its complement is 60 degrees. The rest of the angles that adds up to give us 90 degrees. So complement of an event is the probability that an event did not occur. Probability is based out of percentages. It's 100% probability that something is going to happen. So if the probability of an event occurring is some percentage, the probability that an event does not occur, its complement is 100 minus the probability that it occurred. So that's where the 1 minus probability that it did occur. Now this little apostrophe we've got up here, it may say that A complement or A naught, it's sometimes referred to. So just a notation thing. So the probability of not A is equal to 1 minus the probability of A. So it's all the leftovers. So if there's a 30% chance something's going to happen, there's a 70% chance that it's not going to happen. So with that in mind, let's look at example 4 right here. There's a 25% chance of snow on Monday. What's the probability that it is not going to snow? So pay attention to that. So the probability of not snow is equal to 1 minus the probability that it will snow. So if it's 25% chance that it's going to snow, the probability that it's not going to snow is going to obviously be 75%. Now this seems like a very trivial thing, but this idea of complement, that things add up to give you 100 so you can subtract the part from the whole, is a very useful thing that we'll often refer to in math. Just kind of think of how it can make your life easier. If I want to know the probability of something happening and the something is very, very likely to happen, it doesn't make a lot of sense. Think experimental probabilities. It doesn't make a lot of sense to add up all that stuff that's going to happen and to calculate the probability. Would it not be a lot easier to figure out the few times it doesn't happen and subtract those few times from 100%? So this idea of complement, taking what we don't want and using it to figure out what we do want by knowing that the two add to give us 1, and that's really what it's all based off of. Probability of A plus the probability of not A equals 1, is very, very useful in being able to make the information work in our favor, and we kind of bend it to our will, so to speak. All right, that's part 1 of probability. We've got another lecture that we're going to do on probability. We're talking about binomial probabilities, go a little more in depth with conditional probabilities, and tying all the permutation combination stuff into probability. So that's where part 2 is, so look for that in the future. But for now, that's probability, just basic mutually exclusive, non-mutually exclusive, complements, independent and dependent, knowing the difference between and statements, or statements, and just in general, what is probability? Number of successes, or number of successful outcomes divided by number of possible outcomes. So that's it, and I will see you in class tomorrow, guys.